Hello, we're back, and we're going to be finishing up some of these problems. I just kind of want to, I kind of want to say that that's Roman numeral form. Kind of say sorry for like all the ums and ends. I don't know, maybe I'm a little sleepy, nervous because there's a lot of content I'm trying to cover kind of fast. But I hope you put up with it. Regardless, let us push through and do this. So we're gonna start off again with, I guess, continue where we left off. And this one's gonna be n to the 2n, n plus 1 factorial over 3 to the n factorial. Now, we see factorials, we're gonna think ratio test, so let's do exactly that. Uh, gosh, okay, there we go. So we do the n plus 1 term over the nth term. So we're going to do n plus 1, 2 to the n plus 1. Then we're going to have an n plus 2 factorial in here, all over 3 to the n plus 1, n plus 1 factorial. And I actually just forgot something. We see we have two factorials, one in the numerator and one in the denominator. That can actually be simplified right away. I'm not, just because I already started, but I'd actually recommend doing so. Just makes the problem a little easier. Now we're writing the nth term, and essentially, instead of writing it in the denominator, I'm just flipping it and multiplying it by the n plus 1 term. And that should be that. So now we want to cancel out a bunch of these things. So we're going to take this is equivalent to the limit. Now what can be canceled out? So we're going to have a 2 up here and a 3 down here because these are going to cancel out with each other. We have an n factorial and an n plus 1 factorial, so we're going to have n plus 1 down here, and we're going to have an n plus 2 up here. And then we have an n and an n plus 1, so we're going to have n times n over, oh, I did that the wrong way. It doesn't really matter, but n plus 1 over n. That should be correct. Yeah, okay, I thought we were doing a different type of problem for a second. This should be right. And we have to remember what the ratio test actually entails, so I don't want to mess up again, so I'm just going to quickly go check. It converges if it's less than 1, diverges if it's greater than 1, and then if it's inconclusive, if it's equal to 1. So we want, ideally, it would be greater than or less than. There it is. And what we're going to see is that this limit is equal to 2/3. I'm just going to kind of cut to the chase right there. This is equal to 1. This is equal to 1. Obviously, has the limit as n approaches infinity. So we're just going to have 2/3, which is less than 1, and therefore it converges. Very cool. What do I want to do? I do want to save a little bit of time. So I was going to go over an example. It was 1 over n squared plus 1. Essentially, we would see that that converges by the comparison test, and it was actually inconclusive with the ratio test. So you can do that on your own if you want. There's also an nth root problem. I don't love the nth root test. I just feel like it's kind of a little boring even. But essentially, we had 2n plus 4 over n minus 1, and that was all to the nth power. So clearly the nth root test is going to work there pretty nicely. Now we'll do this one. It's going to be an alternating series. So we have this. And what we want to do is use our limit test, and quickly we'll review what our limit test is. Oh, that's right, that was all the way up here. That was our nth term limit test. So in this case, that would be our nth term would be, I'm just going to call it denoted by a sub n. That'd be n plus 1 over n plus 2. And that's because we're going to take like the absolute value, I suppose. And now we're going to take the limit of this. And what we'll see is that this is equal to 1. And because it's equal to 1, as we see here, the series would diverge. Just wanted to make sure I got that. That is correct. Okay. So that's that. Not very difficult. Now let's talk about error bound. So this is going to be error bound. Now this one is a little simple, but that's okay. So what we have is the summation from n equals 1 to infinity, -1 to n plus 1 over n squared. And we're going to say we're going to do this for 5 terms. And so what's the error? Now, if you remember, the error is simply less than a sub n plus 1. Now we know that n equals 5 because it's given right there. So essentially we just need to find the sixth term. And in this case, the 6th term would be, also remember it's absolute value, so the negative doesn't matter. The 6th term would simply be 1 over 36. I guess it would be -1 over 36. But then, of course, you're taking the absolute value of that. So that is simply that problem. Error does get a little more complicated at times, but you know, it's okay. Now we're going to do an interval of convergence problem. And we're going to say this, and then x to the 2n minus 1 over 2n minus 1. And we're just going to do the ratio test on this. Whenever you have something like this, ratio test kind of can't hurt. It's always kind of good. So we're going to take the limit, and then that's not what I meant to do, x to the 2n plus 1 over 2n plus 1 times, oh, also since we're taking the absolute value, I'm just ignoring the -1 to the n plus 1 term. Should definitely mention that. Then 2n minus 1 and x to the 2n minus 1. Okay. So we're going to continue with this limit. We're going to cross things out. And what we'll see is that we should have x squared times 2n minus 1 over 2n plus 1, which would be equal to x squared. Yeah, that's correct. So we know that the series converges when x is, or I guess when the limit is less than 1. So we're going to say that the absolute value of x squared is less than 1. And then we're going to take the square root of this. And of course, the square root of 1 is just 1. So the absolute value of x is less than 1, which means that our interval of convergence is -1. -1 is less than x, which is less than 1. And that is our answer. Oh, God, that's not our answer. What we have to do is check our endpoints. And that's, you know, something that can be overlooked because you kind of want to get the problem done with, but it's extremely important. So we're going to say at x is equal to, so our endpoints are -1 and 1. So at x equals -1, we're going to essentially plug in our value. So it would be -1 to the 2n minus 1 over 2n minus 1 over 2n minus 1, and that would be, now we're going to take the limit. It's going to be the limit test. So the limit from 1 over 2n minus 1, and it's negative because we're always going to get an odd number there. This is going to be equal to, should just be 0. And if that's 0, we're going to have this converges. And yeah, that's correct. believe that is correct. Here, let me double check the notes real quick, I guess. That should be correct. So this integral of convergence of this series right here, x to the 2n plus x to the 2n minus 1 over 2n minus 1. Honestly can't find it right now, but again, I do think it's right. It's my bad for, I guess, not being completely prepared. I'm sorry. Okay, here might be. Yeah, okay. Um, what did I say? Yeah, okay, I did it right. I just got nervous, I guess. X equals 1. I'll do the same thing. Now, since it's 1, it's just going to be 1 over 2n minus 1. So we're going to take the limit of that. 1 over 2n minus 1. And again, that's going to be equal to 0. So it's going to converge. And so our final interval of convergence is actually going to be equal to negative 1, is less than or equal to x, which is less than or equal to 1. And that is our final answer. Confident in that. Okay, so that wasn't too bad. A little hiccup, but that's okay. And I think we'll jump to writing a Maclaurin series for a given function. So I kind of like the e to the negative 2x, x e to the negative 2x problem. So what we're going to do at first is just write what e to the x is equal to. Now, if we remember from our nice note sheet, e to the x is equal to 1 plus x squared over 2 factorial and so on. So it's not too hard to remember. Plus x squared over 2 factorial plus x cubed over 3 factorial plus dot dot dot. Now we're going to substitute in our negative 2x. So we're going to have 1 minus 2x plus 4x squared over 2 factorial. We're not going to simplify, even though we could right there. Then it would be minus. We're going to create an alternating series because of that. Minus 8x cubed over 3 factorial, yep, plus 16x to the 4th over 4 factorial, and that would be that. Now we multiply everything by x, and we're going to get x minus 2x squared plus 4x cubed over 2 factorial minus 8x to the 4th over 3 factorial plus 16x to the 5th over 4 factorial. And that would be that. Okay. Now we're going to do our big problem. I just want to check the time. Yeah, we got enough time. Okay, so we did this one in class, but I'm going to go over it again. So we have f of x is equal to 1 over 1 plus x cubed. Now the Maclaurin series is given. I just know that m of x is equal to, or I guess, m of x is equal to f of x is equal to 1 minus x cubed plus x to the 6th minus x to the 9th plus dot 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 plus negative 1 to the n x to the 3n. And the interval of convergence is given as negative 1 is less than x is less than 1. So we have to write our 3 non-zero plus general terms for Maclaurin series, I'm just going to call it MS, for f prime of x. Now that's not particularly difficult. Essentially, we just want to differentiate every single term that we wrote down. So we want 3 non-zero ones. Well, the derivative of 1 is going to be 0, so that's going to be a 0 term. So our first term of f prime of x should be negative 3x squared, and then our second plus 6x squared, plus 6x to the 5th, minus 9x to the 8th, and then now we're going to work on our general solution. So it's going to be the same, negative 1 to the nth power, but now it's going to be 3n x to the 3n minus 1. And now b, so we're going to use a to find the sum of negative 3 over 2 to the, oh god, I can't even read my own handwriting now. Yeah, it's 2 squared plus 6, 2 to the 5th, minus 9, 2 to the 8th. And then we're going to have our general form, negative 1 to the n, 3n over 2 to the 2n minus 1. So what we can see is that we got powers on the bottom, and that's a little interesting because right here we have them in the numerator. But we see that the coefficients are the same, and the powers are actually the same. We have 2, 5, and 8, and then 2, 5, and 8. So this is actually f prime of 1/2, because, if we took the power of 1/2, we can write that as 1 over 2 to that power, which is exactly what we have here. So this sum is going to be, we remember that f of x is equal to 1 over 1 plus x cubed. Therefore, f prime of x is equal to negative 3x squared over 1 plus x cubed squared. And that is our quotient rule. I'm not going to do the derivative. So therefore, f prime of 1/2 would be negative 3 times 1/2 squared over 1 plus 1/2 cubed squared. And I'm not going to evaluate that, but that's the answer. So now we want to find 4 non-zero terms of the integral from 0 to x of f of t dt. So just like we differentiated the terms earlier, now we're going to integrate them. So we're going to get, essentially, we want to integrate every single term of this series. So the first one's going to be 1. The first term is 1, which is now going to become x. Then it's minus x cubed, which is x to the 4th over 4. Plus x to the 7th over 7, minus x to the 10th over 10. Now, of course, our general solution, between negative 1 to the n, that doesn't change. And then x to the 3n plus 1 over 3n plus 1. And that's it. Not very difficult. Now for d, we want to use the first 3 non-zero terms to approximate the integral from 0 to 1/2 now of f of t dt. And then the second part to that same problem is what properties of the integral from 0 to 1/2 f of t dt guarantee that the approximation is within 1 over 10,000. So first we're going to, write our first 3 terms. And remember, our x is essentially 1/2 now. So we're going to have 1/2 minus 1/2 to the 4th over 4 plus 1/2 to the 7th over 7. And that's actually it, like that. Therefore, we see that we have our alternating series. So our error is going to be less than the next term. And that next term is going to be 1/2 to the 10th over 10, which is equal to 1 over 2 to the 10th over 10, which is also equal to 1 over 1024 times 10, which is clearly less than 1 over 10,000. And that is our answer. I think an important distinction to make is that we use the approximation or the error bound for an alternating series, because clearly the series is alternating, versus the Lagrange error bound. And I think once you understand when to use which one, it's not very difficult to solve these types of problems concerning error bound. But yeah, that would be that. We went over a decent amount of problems. Honestly, I'm frankly exhausted right now. And so if you see this video before the test, I wish you the best, and I'll see you later.